The sun has been a significant area of strength for us, especially of late, and it is about to undergo a basic yet fascinating change, the inversion of its magnetic field. This process occurs roughly every 11 years, marking the midpoint of the solar cycle, and has broad repercussions for us here on Earth. In fact, this solar activity could soon present a serious risk, potentially causing complete disruption and catastrophe for everyone on the planet. As you will find, the sun's magnetic field is generated by the movement of electrically charged gases in its interior, a cycle known as the solar dynamo. Over the long term, this magnetic field becomes increasingly tangled and reshaped due to the sun's rotation and convective changes. Ultimately, this process leads to the inversion of the sun's magnetic poles, where the north magnetic pole changes into the south and vice versa. So, what exactly happens during this cycle? The sun is primarily composed of hydrogen and helium in a plasma state, where electrons are not bound to atoms, resulting in a mix of free electrons and ions. The sun's interior is divided into several layers: the core at the center, the radiative zone, and the convective zone. The core is where nuclear fusion takes place, converting hydrogen into helium and producing immense amounts of energy. Above the core lies the radiative zone, where energy is transferred outward through radiation, though energy moves slowly here, as photons are absorbed and re-emitted by the solar plasma. The outer layer of the sun's interior is the convective zone, where energy is transferred by convection. In this zone, hot plasma rises toward the surface, cools, and sinks again, creating convection currents. The solar dynamo process primarily operates in the convective zone and in a thin layer known as the T-line, which lies between the radiative zone and the convective zone. The T-line plays a crucial role in generating the sun's magnetic field, as it is where the sun's differential rotation and shear flows contribute to the field's creation. Here's something interesting. The sun doesn't rotate as a solid body. Instead, different parts of the sun rotate at different rates, with the equator turning faster than the poles, a phenomenon known as differential rotation. This differential rotation stretches and twists the sun's magnetic field lines, elongating the magnetic field. The solar cycle lasts approximately 11 years, during which the sun's magnetic field undergoes a series of changes, culminating in the inversion of its poles. The cycle begins with the sun in a state called solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field at this point is simple and bipolar, with distinct north and south magnetic poles. As the cycle progresses, the number of sunspots increases. Sunspots are areas of intense magnetic activity, and their appearance signals rising magnetic activity from the sun's interior. These sunspots appear in pairs with opposite magnetic polarities and gradually move toward the sun's equator over time. At the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity with the highest number of sunspots, solar flares, and coronal mass ejections, CMEs. During this phase, the sun's magnetic field becomes increasingly complex and tangled due to continuous twisting and shearing from differential rotation and convection. As solar maximum fades, the magnetic field begins to reconfigure itself. The twisted and tangled magnetic field lines reconnect, and the global magnetic field gradually reverses its polarity, switching the north magnetic pole to the south and vice versa. After the pole inversion, the sun enters a period of declining activity, returning to solar minimum. The cycle then starts again. Currently, we are in the solar maximum stage, and the sun's magnetic field is about to flip. During this phase, we can expect solar activity that is as hazardous as it is fascinating. However, the sun's magnetic field inversion is not a sudden flip. Rather, it is a continuous process. As the solar cycle progresses, the magnetic field undergoes gradual changes. At a certain point, the magnetic field becomes so twisted and tangled that it reaches a tipping point and begins to reconfigure itself, leading to the pole inversion. So, do we know when the sun's magnetic field will flip? Researchers continuously monitor the sun's magnetic activity using various instruments and techniques. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed images of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, measure the sun's magnetic field and track changes over time. One key sign of an impending magnetic inversion is the behavior of sunspots. During solar maximum, sunspots appear more frequently and become more pronounced as they move toward the sun's equator, a sign that the magnetic field is becoming increasingly unstable and preparing to flip. While we're on the subject, let's dive deeper into sunspots. When the sun's magnetic field lines become twisted and tangled due to differential rotation, the sun's equator rotates faster than its poles, causing the magnetic lines to stretch and curve. When these lines loop over the sun's surface, they suppress the convective motion of hot plasma from the sun's interior, resulting in the cooler, darker patches that we observe as sunspots. Sunspots are not just fascinating. They can also produce powerful solar flares and CMEs. These phenomena release huge amounts of energy and charged particles into space. When directed toward Earth, they can disrupt satellite communications, affect power grids, and pose risks to astronauts in space. Additionally, increased solar activity can enhance auroras, but it can also raise radiation levels in Earth's upper atmosphere. Now, let's examine the difference between solar flares and CMEs. While both are massive bursts of energy from the sun, they differ fundamentally. Solar flares are sudden, intense bursts of radiation caused by the release of magnetic energy associated with sunspots. They emit enormous amounts of energy and light, often as X-rays and ultraviolet radiation. Think of them as eruptions of bright light and heat on the sun's surface. In contrast, CMEs are enormous releases of solar wind and magnetic fields from the solar corona. These are essentially giant bubbles of gas and magnetic fields ejected into space. When a CME occurs, it sends billions of tons of solar particles into space at incredibly high speeds. Although solar flares and CMEs are linked, they are not the same. A solar flare can occur independently, but sometimes an extremely strong solar flare is accompanied by a CME. In terms of potential hazards, solar flares can disrupt radio communications, navigation signals, and pose a significant risk to astronauts in space due to intense radiation. However, CMEs can have a broader impact. CMEs can cause geomagnetic storms that disrupt power systems, satellite operations, and navigation systems. They can also enhance auroras but pose serious risks to Earth's technology and infrastructure. Another consideration is that during times of high solar activity, the amount of high radiation reaching Earth also increases. Satellites and other space vehicles are particularly vulnerable to elevated solar activity. The charged particles from the sun can damage electronic components, disrupt communication signals, and even alter satellite orbits. Beyond harming technology and infrastructure, what else can happen to the planet? While the sun's magnetic field inversion doesn't directly affect Earth's atmosphere, the related changes in solar activity can impact Earth in several ways. Some studies suggest that variations in solar radiation can influence climate conditions and weather patterns. For example, increased solar activity can lead to a slight warming of Earth's atmosphere, potentially fueling existing climate change. Could auroras be the only positive aspect we experience here on Earth? Perhaps. One of the most striking impacts of increased solar activity is the enhancement of auroras. These natural light displays, known as the northern and southern lights, occur when charged particles from the sun interact with Earth's magnetic field and atmosphere. During times of high solar activity, auroras become more frequent and can be visible at lower latitudes, offering dramatic nighttime shows. However, aside from the beautiful auroras, there are also more concerning aspects of the sun's magnetic inversion that could occur if we are unprepared. One primary risk is the increased likelihood of geomagnetic storms. These storms occur when solar wind overloaded with charged particles interacts with Earth's magnetic field. In extreme cases, they can cause widespread power outages and damage communication infrastructure. One such event occurred on the morning of September 1, 1859. Astronomer Richard Carrington was observing the sun through his telescope as he had done many times before, but on this particular day, what he saw would go down in history as the first recorded solar storm. At 11:18 a.m., Carrington saw a brilliant flare of white light emanating from a group of sunspots. This event, now known as the Carrington event, marked the beginning of the largest geomagnetic storm ever recorded. The white light Carrington observed was a massive solar flare, an intense explosion of radiation caused by the release of magnetic energy in the sun's atmosphere. This flare triggered a massive CME directed toward Earth, which reached our planet in just 17.6 hours, an incredibly short time considering the sun is 93 million miles away. When the CME hit Earth's magnetosphere, it triggered a strong geomagnetic storm. The effects were swift and widespread, disturbing Earth's magnetic field and inducing currents in the ground. Telegraph lines used for global communication at the time experienced severe disruptions. Sparks flew from telegraph machines, operators received electric shocks, and some telegraph stations even caught fire. The induced currents were so strong that operators could send and receive messages even after disconnecting their batteries. One of the most striking and visible effects of the Carrington event was the brilliant display of auroras. The auroras were so bright and extensive that they were visible far beyond the usual polar regions. People as far south as the Caribbean, Mexico, and Hawaii reported seeing the sky lit up with vibrant colors. The auroras were so intense that they illuminated the night sky, allowing people in the northeastern U.S. to read newspapers by their light. In the Rocky Mountains, gold miners were reportedly stirred by the brilliance, mistaking it for dawn and beginning to prepare breakfast. People described the sky as glowing with red, green, and purple hues, shifting and shimmering across the horizon. Now, imagine if a solar storm of the magnitude of the Carrington event were to hit Earth today. The results would be catastrophic. The sun is undergoing a massive transformation. The reversal of its magnetic field, a process that occurs roughly every 11 years as part of the solar cycle. This event, driven by the solar dynamo, could have sweeping consequences for Earth, potentially causing disruption and disaster. The sun's magnetic field is produced by the movement of electrically charged gases in its interior, creating a complex magnetic field that eventually switches its polarity. The sun is primarily made of hydrogen and helium plasma, with energy produced by nuclear fusion in its core. This energy is transported outward through the radiative zone and then by convection in the outer layers. The solar dynamo, which operates in the convective zone and the T-line, generates the sun's magnetic field. Differential rotation of the sun, where the equator rotates faster than the poles, stretches and amplifies the magnetic field lines, driving the solar cycle. Currently, the sun is in the solar maximum stage, where sunspots and solar activity are at their peak, potentially causing risks such as solar flares and CMEs that can disrupt satellite communications, power grids, and pose threats to astronauts. Researchers monitor the sun's magnetic activity and sunspot behavior to predict when magnetic field inversions will occur. Sunspots, which result from tangled magnetic lines, can produce solar flares and CMEs, both massive releases of energy that affect Earth in various ways. While solar flares release radiation, CMEs release vast amounts of solar particles into space. These phenomena can enhance auroras but also pose serious risks to Earth's technology and infrastructure. The sun's behavior is a fascinating interplay of physics and natural phenomena that affects not only our solar system but also life on Earth. Understanding the complexities of solar activity is crucial, especially as we continue to rely on technology that can be affected by solar events. The sun generates energy through nuclear fusion, converting hydrogen into helium and producing immense amounts of energy in the process. This energy travels through the various layers of the sun, eventually reaching the surface and radiating into space. Solar activity can manifest in many forms, including sunspots, solar flares, and CMEs. Sunspots are cooler regions on the sun's surface caused by magnetic activity, appearing as dark spots. These variations in solar activity follow an approximately 11-year cycle known as the solar cycle, with periods of high activity, solar maximum, followed by quieter periods, solar minimum. During solar maximum, the number of sunspots increases, leading to more frequent solar flares and CMEs. Solar flares are sudden bursts of energy that emit radiation across the electromagnetic spectrum, including X-rays and ultraviolet light. These intense eruptions can disrupt radio communications and pose risks to astronauts in space. CMEs, on the other hand, are massive ejections of solar wind and magnetic fields that rise from the solar corona and are released into space. When directed toward Earth, these releases can cause geomagnetic storms that disrupt the planet's magnetic field. These storms can lead to beautiful auroras, but also cause potential disruptions to technology. The impacts of solar activity extend beyond space. They affect Earth's climate and surface. Studies suggest that variations in solar radiation can influence climate patterns, potentially contributing to weather phenomena. Increased solar activity can also lead to atmospheric warming, a major factor in discussions about climate change. Moreover, the potential for technological disruption due to solar storms cannot be underestimated. A severe geomagnetic storm could damage electrical systems, disrupt satellite operations, and affect navigation systems. Preparing for such events involves monitoring solar activity and developing strategies to mitigate their impact on infrastructure. Scientists continue to study the sun's magnetic field and its cycles to better predict when significant solar events may occur. This research combines ground-based and space-based observatories that track sunspots, measure magnetic fields, and analyze solar wind. With advancing technology, our ability to predict solar activity improves, which is essential for protecting our technological infrastructure and ensuring the safety of astronauts as we explore space. As we study the sun, its influence on Earth becomes increasingly clear. From the stunning displays of auroras to the potential challenges posed by solar storms, the sun remains a powerful force in our solar system. Understanding its cycles and behaviors not only advances our knowledge of space science, but also enhances our preparedness for the effects of solar activity on modern life.